Well, good afternoon, friends, and welcome to Zoom Time Knowledge. This is a free public presentation series hosted by the James Madison University Lifelong Learning Institute. My name is Rodney Wolfenbarger. I serve as director for the program. I'm also joined by my friend and colleague, Sue G. Sue is program assistant for the Lifelong Learning Institute. And we have the pleasure of hosting our featured guest presenter today, Dr. Anca Constantin, who is an associate professor in JMU's Physics and Astronomy Department, where she teaches physics and astronomy classes and conducts research on galaxies that host supermassive black holes in their centers. Professor Constantin received her Bachelor's of Science in Physics at the University of Bucharest and completed her Ph.D. in Astrophysics at Ohio University. She held postdoctoral positions at Drexel University and the Harvard-Smithsonian Center for Astrophysics before joining JMU in 2009. Her galactic investigations involved identifying telltales of the processes by which black holes form and grow. Anca takes tremendous amount of joy from engaging the public in scientific discovery. And Dr. Constantin, I want to thank you for volunteering your time today and for being willing to share your knowledge with our learning community. Sue and I will be here to support you in whatever way you need. But at this point, I'm going to turn it over to you, and you'll be in control of our presentation until we get to the Q&A portion to follow your presentation.
Thank you so much for the introduction. Hello, everybody. I'm really grateful to have an audience. I am, as Rodney said, I do have a passion of telling everybody about what I'm studying, about our place in the universe, and it turns out that our universe is big as it is. It's really I mean, we can't really talk about the universe and the things that it comprises without talking about the black holes. And I'm sure you have heard about them. Maybe this is why you're here today, to find out how we actually find the evidence for these exotic things. And also just hear maybe over and over again that the black holes are actually quite deceptively simple systems and yet incredibly complex. So that's the reason for which, of course, we're not going to go into every single detail, but of course I am going to welcome your questions at the end, and I'm going to strive to find good answers for that. And I say that because I'm by no means knowing everything there is written or unwritten under the sun, some might say, but in this universe about black holes. I know a little bit because I've studied them for quite a while. I know physics that is involved in, basically their definition and how we understand what they are and how they form, how they kind of came to be, how we came up, we astronomers or human beings came up with this idea of a black hole. And so I'm going to touch, I would say, just a little bit about this, but again, keep in mind that you can ask many other questions about this. And then I really, really want to share with you how we astronomers or the human beings are actually able to identify them. And in particular, the black hole that exists in the center of our own galaxy, because it turns out it's actually one of the easiest among all the billions of black holes that are out there, which we have tentative evidence for. And so this is what, it's the work that won the Nobel Prize for these three people: a German, Rainer Genzel, the American Wonder Woman, Andrea Ghez, and it totally slips to me, and Billingham is going to kind of laugh hard about this. The theoretician who actually worked very hard in putting together a mathematical model for how black holes work. That was a mere, a few years after, and his whole life after Einstein put out there the idea of their existence. So it was just about 100 years ago, right? This idea of the black holes. So I said, right, black holes are deceptively simple in a sense that you can actually put the definition into one sentence, right? You've probably heard things are called black holes because they have a mighty strong gravity, so strong that not even the fastest thing that we have been able to measure so far, which is the light, can escape. So nothing can escape. And if light cannot escape, which is has fastest, is the fastest, and it has the most energy that would make it capable of escaping the pull of the black hole, then what else is going to be out there? So I have here just a few examples just to illustrate for you the strength of gravity and how that does relate with how and when things escape. So for example, here's the Earth and the little ball, which you might recall, it has a diameter of a few tens of kilometers, right? So that's marked here is it's the radius. And so you probably heard about the astronauts, but they did not really escape. They were actually able to come back. But if you really want to go away from the Earth and not come back, you truly need to launch yourself with a speed of about 11 kilometers per second. So that's kind of huge. I can tell you, I should have been able to, that's a lot of miles per hour. Thousands to the so millions of miles per hour. Okay. And so now here's what we're going to do. We're going to do a little experiment, and we're going to shrink the Earth by a factor of 100, right? So we're going to shrink it. It's going to be just about 65 kilometers in radius. Okay. So that's probably the size of our town. And so because of that, of course, this whole mass of the Earth is going to be concentrated in a much smaller volume. And so the density of matter is much higher. We're not going to go into the numbers of what that is. But anyway, that translates into an escape velocity. So in this case, right, because the Earth now is much, much smaller, you would need to actually travel at a speed that is 10 times larger. So it was already a tremendous amount of energy that you needed to escape Earth in the first place. Well, I mean, that's probably a good thing, because otherwise we wouldn't be able to walk on the surface of the Earth. But now make the Earth even smaller, so maybe a third of an inch. Well, guess what? If the whole mass of the Earth is going to be put into a tiny marble of a radius of 1/3 of an inch, right? So that's a lot of mass. It's a really highly concentrated in mass thing. Anything on the surface of that little marble would be really stuck thanks to the gravity of that marble. So in order for anything to basically be able to make a tiny leap, would need to travel at a speed that is close to 300,000 kilometers per second, which is the speed of light. So, really, another, what is it that keeps these things so strongly together, and what is it that makes everything around it, so hard to escape? It's pretty much summarized in this picture, right? And of course, the mystery of that has been a little bit revealed to us by the 2020 winners of the Nobel Prize for Physics. That looks like they found while they were traveling towards the black hole, because that's the only way you can actually get to see. And it turns out you're not going to be able to share that information with anybody, because every information that we have about what's happening in the universe is through the information that light carries. And so if the light doesn't escape, we're not going to actually get to know what's happening inside the black hole. So whether that is a lot of unmatched socks or not, I guess we're gonna have to answer it in the next hour or so. Okay, so now let's see. I searched a little bit the dictionary for answers to this question, like what is the black hole, right? Because this is what we do when we want to find out what this and that things are. So here are a few definitions. It's a region of space resulting from the collapse of a star. Well, that could be true, but it's not the only one definition. There's a region of space with a strong gravitational field. Also true. Some might call it a dungeon or a dark cell in a prison, or maybe a project that requires large effort with no return. I'm sure other people have used the idea of black hole or the name of as a black hole for all kinds of other things. What we're going to mainly be discussing about here is, and what I want you to have in mind when you think about black hole, is a concentration of mass with a really strong gravitational field, so strong that not even light can escape its grip. So it does turn out that theoretically, these black holes are believed to be associated with the death of massive stars. And I have here actually a tiny picture that shows in the left upper corner, it's a clouded gas where we believe, gravity wins and forms stars of various masses. And now we have, in those stars form, but they evolve differently depending on the mass they start their evolution with. And it's the massive ones, stars that are at least 30 times more massive than the sun, or just 10 times more massive than the sun, that they're going to become red giants and explode as supernovae and leave behind something that we cannot see, but we can feel the gravity of. And it turns out that just about 60 years ago, there was this discovery of an object in the sky that looked like a star, but it was not a star at all. And the discoverer was Martin Schmidt. He took the spectrum, he stretched the light that was coming from that tiny, boring object that looked like a star, right? So just a point source of light, and realized that there is no explanation for that type of light, and some other crazy things that found in that stretch of light that would match the nature of it. And it turned out that the only explanation was this gas that is swirling around something so massive that it needs to be at least a few millions to billions of times the mass of the sun. And the light that we see from that object is actually coming from this so-called accretion disk, that is matter that is swirling around the supermassive black hole now, because it's millions of times the mass of a normal star. And it's through the viscosity and through the fact that charges are accelerated at speeds really close to the speed of light that emit the light that we see from that tiny volume. So it's a lot of mass concentrated in there. So that was basically the discovery of something that cannot be explained by anything but the supermassive, but by a supermassive black hole. But now, of course, we're thinking, how real are these things, right? And so that was, and later on with images from the Hubble Space Telescope, we found that those point sources that cannot be explained by anything else but accretion of matter onto supermassive black holes live in galaxy centers. And so now we can talk hours and days about, theoretically what these black holes or supermassive black holes are, just how exotic they are. But as I said, I find fascinating the story of how we got to obtain irrefutable evidence for their existence. And so I'll tell you a little bit about how Andrea Ghez and Reinhard Genzel found out about the existence of a black hole that is 4 million times the mass of the sun in the center, in the heart of our own galaxy. And all this work started in the early 1990s, where so we have the German team was performing observations with the New Technology Telescope at La Silla in Chile. And just a few years after that, it was Andrea Ghez. She started kind of alone, just a freshly hired assistant professor at UCLA, said, okay, let's use the newly built Keck telescopes. That was in the 93, 96, high atop Mauna Kea volcano on the Big Island in Hawaii. And they were doing this for the same goal. What they wanted to do was to pinpoint the location of the galactic center. You might have seen images of galaxies and you think, yeah, the center of the galaxy is there. Of course, they wanted to see where the gravitational center of the galaxy is, if there is a center, and what happens in the center of our own galaxy, our home galaxy. So it turns out that just about that time, so in the early 90s, with the help of the Hubble Space Telescope, scientists found that in the center of another galaxy, a giant elliptical one called, can you guess, it's actually a really famous galaxy. It's M87. You probably have heard of it, and I kind of put in a corner a tiny image of it. It was later imaged by an array of telescopes. I'm going to come back to it because it is important. So that was just 2 years ago. But in the early 90s, with the Hubble Space Telescope in particular, scientists were able to measure how fast the gas was moving close to the center of this galaxy. And it turned out to be about 3 million miles per hour. And that allowed them to measure the mass of whatever was in the center that kept the gas moving that fast. And they found that that should be about 4 billion times the mass of the sun. So now their measurements, it was the first of its kind, and it pinpointed to the existence of a obviously supermassive black hole. But it did not conclusively prove its existence. So yes, now we know that there is a supermassive black hole in there because, especially because we did obtain this image of it. And so what you see here is the gravitational bending of light around the edges of that supermassive black hole that makes it basically impossible to observe the hole itself as a black dot superposed against the bright background of its gas that is swirling around. So what we're seeing here actually is called the ergo region, where light is curved and pulled around the black hole. But I wanted to draw to your attention the scale, right? So here we have, we're actually never going to be able to see inside a region that is maybe a few times the size of our own solar system. So I overlaid on the image of the very center of that galaxy, the orbit of Pluto, which kind of is the size of our own center of our own solar system. So we have the sun and then all the planets. Some of them 4 are really close to the sun, and then we have the gaseous planets, and then Pluto, which is not a planet, it's one of the 1,000 dwarf planets. And then also you can see here the location of Voyager as it was, I think, about 2 years ago. So really that is a large distance, right? There are many things that could still happen inside a supermassive, especially a supermassive black hole. So 4 billion times the mass of the sun are concentrated into that area. But anyway, so back on Earth, because I really want to go into this story in history about how we were able to, or they were able to really prove that there is a supermassive black hole in the center of our galaxy. So here's the thing: back on Earth, when both the German and the American teams continued to peer through the thick clouds of gas and dust that basically covered the center of our galaxy, because they really wanted to go into the assumed monster layer to see what is there. It was not an easy task. And let me give you a little bit of a background of what happens in the galactic center. And actually, on a good summer day, say you go out there in a country and you look at the sky, and you're most likely passionate about astronomy and looking at the stars, and you see that spill of milk, the Milky Way, but you do see that is kind of covered by lanes, by dark lanes. Those are lanes of dust. Okay, so even in, like, when we talk about the center of the galaxy, we're talking actually about, and I say here, the inner 500 parsecs. So I probably should have used maybe the light year, so multiply that by 3. So it's really not easy to pinpoint exactly what's happening, and mainly that is especially with just a binocular or even a telescope, and that's going to be an optical telescope or a telescope that works with visible light. It's hard because there's a lot of extinction. Okay, so optical studies are actually impossible. So that's why we need to go to longer wavelength, to light that can go around the particles of dust, the dust bunnies that exist in space. And there, it's a pretty dense region of dust bunnies close to the center of our own galaxy. So we use radio and infrared. We also observe ionized gas, line emission. So it's actually a lot of things that happen at the star clusters of stars. And it turns out that the stellar density is pretty high. So I said 10 to the 7. So that means 10 millions of stars per a few light years a cube. Okay, so now compare that with the same units, but it's going to be just 0.1 stars per a few light years, which we kind of know because the closest star to our own solar system is just a few light years away from us. So basically what that means is that if the sun were near the galactic center, that's what I mean by the GC, the nearest stars would be just kind of around the corner. And I have here the AUs, the astronomical units. So the nearest star would not be just a few light years away. It would be just a few solar systems away from us. And basically, instead of just calling Sirius the brighter star in the night sky, there will be millions of stars, just like Sirius. And the total starlight would be more than 200 times brighter than the full moon. So we wouldn't have nighttime, basically. Right. So I said, really, the scientists needed to go to longer wavelength, to infrared or radio. But the infrared is actually the key wavelength or the type of light that was used. And another key thing was also a new technique, which is called adaptive optics. So what astronomers needed to do, right? So you're obviously aware that there is an atmosphere, a layer of all kinds of molecules that protect us actually from any kind of electromagnetic radiation that is emitted or travels around our planet. So it's good for us as long as it has the right concentration of various types of molecules. We're not going to go into into that now. But it turns out that those molecules also have, they scatter the light that's coming from everywhere in the sky. And so when the light comes through the atmosphere, it's going to dance around through the molecules before it comes into our telescope. And so what that does is it's blurring the images. And in order to peer into the very center of our own galaxy, to measure exactly what the stars do, because that's what these people wanted to do, you really needed a really sharp image. So what they did, they made their own star, okay, through a laser. They made the laser stars. These are images from the twin Keck telescopes that shoot a laser in the sky, and then they're able to trace the dance of that laser in the sky, and then use that trace to correct the images that that they take from that portion of the sky. And I have here actually a really nice image of the pioneers of the adaptive optics technique. And one of them is actually the one of the Nobel Prize laureates. You probably recognized Andrea, it's in the center. And then the man, I think was later the director of the Keck observatories. And then we have Claire Max, who is truly a pioneer of the adaptive optics technique. So that's another beautiful image of the Keck 10-meter telescopes, the twins that point the laser stars towards the center of the galaxies. You see a beautiful image of the Milky Way, and somewhere there is this Sagittarius A, which is the location. We have name for that location of the center, or close to the center of the Milky Way. And here's what they were able to do. I said they corrected for that dance of light that comes through the atmosphere. So now is the blurred image of the stars, right? So somewhere is the center of the galaxy. They need to find it by just tracing the motions of the stars. So now is adaptive optics off, an image of that region of the sky without adaptive optics, and then with adaptive optics, everything comes suddenly into focus. So it's good to have that kind of comparison. So now they had the means to measure what's happening in the center of our own galaxy. Now, this region was actually part of a much larger effort, and I wanted to tell you about this. There are complex investigations of the larger terrain of the galactic center in search for clues of the origins of our own galaxy, or the things that might exist in the very center of our own galaxy. So people looked into radio emission, and they found some bent filamentary structure. They've seen the same thing in infrared. And so there are all kinds of physical processes that reveal to us that things are very hot. Things are related to very energetic phenomena like supernova explosions. And when I say hot, that is millions or more degrees. So there are really some things happening in the center of our galaxy, and I can tell you that's pretty quiet compared to some other types of galaxies that are called active galactic nuclei. So whatever happens in the center of our own galaxy, if there is a supermassive black hole that is snacking around, then that's actually pretty quiet, but it's there, okay? And so what they also found was that, okay, there is something really energetic happening. There must be a swarm of at least 20,000 black holes that lived in the inner, just a few, less than 10, maybe just about 3 light years actually. And so it's actually kind of hard, even theoretically, but it's kind of hard to have this kind of system survive for as long as this center of the galaxy seemed to survive. So what was needed to be done now was to confine this mass. So they found the mass. They said, okay, there is this much mass, and it's dense material. This must be neutron stars or really small black holes. Maybe there is no such thing as a supermassive black hole. Maybe there is just a few tenths of thousands of smaller black holes, because it's kind of hard to wrap our mind around one single thing that is, a million times more massive than the sun, because we do have evidence for stellar mass black holes. So their search continues, and now what needed to be done was actually to confine this mass to as small of a volume as possible, right? Because if you compress all these tens of thousands of neutron stars or black holes together, they're just not going to survive. They need to be only one single thing. And so what they did, it was snap pictures, and that was like thousands of pictures in a really short time of everything that happens in the galactic center. So I have here an example, and these are on the smaller panel on the left of the screen. Okay, so these are thousands of images of stars that are moving in the galactic center. These images were obtained with the adaptive optics. Without adaptive optics, there's no way we would be able to see the individual stars. And then, of course, because the atmosphere is in motion, the apparent motion may shift from image to image. But anyway, they calculated the speeds of the stars and their rough trajectories around center that allowed them to pinpoint the exact position of the center, as well as how strong of a gravitational pull that has. Okay, and so there's not a single object that is known to weigh that much. Okay, but still, it did not rule out a dense concentration of stars that were packed into the center that held together, that is held together by their mutual gravity. It turns out that the proof came from an extraordinary event, and I can let me run this other little video that shows the orbits of stars, and I want you to look for one in particular, this SO2, and look at how it moves. So it goes around, but at some point it goes really close to the center, which now is marked by a little star. It goes really, really fast. And so it's thanks to that. So now it's going to go again. You see how it speeds up. Okay, so the models say, okay, what if we catch that star SO2 going when it's going really close to it? That is actually going to tell us exactly how much mass is in there that keeps this star orbiting, pretty much like how the sun keeps the planets orbiting around it, right? So, for example, if you just put a black hole instead of the sun at the location of the sun, a black hole with the same mass, just one solar mass, nothing would happen to the orbit of the Earth. Nothing. I mean, yeah, we would not have the warmth and the light that's coming from the sun, but in terms of the orbit of the Earth or any other planet around the sun, nothing would happen as long as there is that same mass in the location of the, say, center of the Earth. So the final proof actually came just about 2 or 3 years ago from an extraordinary event. So we're gonna maybe watch again what's happening with the star SO2. Okay, so actually the first one happened in 2002, and then in 2019 actually came again, and the astronomers were able to probe the general relativity and all the mathematical predictions about how the black hole behaves. But in the spring of 2002, the star SO2 made a dramatic move. Okay, so maybe this animation doesn't make justice, but what you're seeing here is the fact that this star has been accelerated to 3 million kilometers per hour, and it's really very close to the location of the center of the galaxy, what seemed to be the center of what keeps together all of these stars in their orbits. And the mathematical model fits the data and the exact location of these stars beautifully. Now, this thing is, what this data proves is that if there were a swarm of stars in there, then that star SO2 would have wobbled. But it did not. It went beautifully on the path that was predicted mathematically to go through. And the only explanation was, and it was without a single doubt, that thing that keeps the stars in orbit was a single thing, one single black hole, and that was as massive as 4 million times the mass of the sun. So, so these are images that come from the Keck telescope in Hawaii. But actually, the Germans with a very large telescope in the northern Chile, they found very similar things. And then later on, there have been some X-ray follow-up, and they there have been some other additional measurements of maybe the size, what we call the size of the supermassive black hole, and that constrained even better the location and the size and the observations and the flares and the rapidity of the flares, and that indicates that matched that mass of the supermassive black hole in the center of our own galaxy. So I have here another little video also from the UCLA group, and now we have here data that is spanning. So they put together all of the observations of all of the stars in the galactic center, but now you see the earlier observations were from a little further away regions, not really close by, and we still see the stars orbiting around something. So the gravity of that thing in a center, which we don't see, it is strong enough to keep around stars, not just really close by in closed orbit, but also far away as well. So this is like every 2 years per second, you're seeing the motion of the stars. And yes, there are some colors involved in this diagram, and that has to do with the ages and the types of the stars that are there. So there's a lot of physics and some other phenomena that these people are after, because they're trying to understand what kind of stars exist in the swarms of stars that do this dance around the supermassive black hole in the center. So you might wonder, okay, why do we need to know maybe about these supermassive black holes? And yes, we did find irrefutable evidence for the one in the center of our own galaxy. But I also told you about evidence, maybe not as direct, because that galaxy M87 is really a lot further away than the black hole in the center of our own galaxy. We do find, the more we look, we find evidence for the fact that there is a supermassive black hole in the galaxy center, and the rounder the galaxy is, actually the more massive the supermassive black hole in its center is. Okay, so basically what I say here, the black hole correlates with the host property. So this is what this graph shows. The black hole is higher for galaxies that have more pronounced bulge in its structure. You probably have heard about spiral galaxies and elliptical galaxies, and you might recall that our own galaxy, it's like a flat pancake, so it's going to be close to the no black hole. So it's basically one of the smallest supermassive black holes that are out there. But there are some others, like the one in M87 that would be in the upper right corner in a graph like this. And so what these findings tell us is that the supermassive black hole in the center kind of knows about its host galaxy. And so that prompted us astronomers to look into ways in which we can explain the existence of these supermassive black holes. So we do know about the stellar black holes. Yes, a high mass star is going to explode as a supernova and leave behind a stellar mass black hole. But how in the world, how in this universe, we get to form in relatively short time, just a few, maximum a few billion years, you get to increase the mass of such a thing from a few solar masses to a few millions, if not billions of solar masses. So anyway, this is like real data. We wanted to show you, we do measure stuff about galaxies and how stars form. So that's on the x-axis, and then the black hole mass calculated from models on the y-axis. So so we one of the maybe most important, I know one very important question in astronomy nowadays is really trying to understand which one was the first, kind of like the chicken and the egg idea. Was it maybe a supermassive black hole that was first formed by hierarchically grouping together smaller black stellar mass black holes that formed a higher and higher masses of black hole that through accretion would gather around stuff that maybe formed the galaxy, or maybe it was first the galaxy that was just basically an ensemble of stars, and some of those were the high mass stars and evolved the supernovae and left behind the stellar mass black holes that later on coalesced to form eventually in the very center of that galaxy, the supermassive black hole that we find evidence for. So this is basically, I'm working on some aspects of this question. So if you want to ask me about that as well. I think I wanted to stop here, but I'm happy to take questions maybe about black holes in general, or how we actually got, or especially these wonderful people who got the Nobel Prize this past year for physics for their discovery of the supermassive black hole in the center of our own galaxy. So thank you, and I'm saying thanks here with the images of galaxies. They're from the Sloan Digital Sky Survey, which I encourage you to go check it out, so you can write your cards with galaxies as well if you're so inclined. But thank you.
Dr. Constantin, thank you for your presentation, and again for sharing your knowledge and expertise. There are a few questions in the chat window, and I don't know if you have access to your chat window.
No, but I can stop sharing and maybe, I can see them.
Okay,
Great.
because some of them are a little technical, so I wanted to repeat them in case people cannot see their chat window. They will know what we're responding to. And then I will open the microphones up for people who have questions, comments, feedback, or would like to continue the discussion. The first one here that we received, I'll go in order, and I'll just read it to you. You can see it as well. It says, as a star collapses, thereby increasing its density, does that mean that all its atoms are compressed, the space between them becoming infinitesimally small? If so, why does the compression not result in atomic fission and/or fusion? And if it does, why would the resulting energy from the explosion not work against the collapse? Is it a matter of gravity overcoming any countervailing force? So I understand all the words in it, but that's why I wanted to repeat it to you, because I hope you understand the nature of those questions. A lot of complexity there to unpack.
Yeah, that's a great question. So I'm going to try to address, there are quite a few things here. So when a star collapses, it's actually just the core of the star that collapses. So the star starts with basically 98%, at least 98% hydrogen and helium. And there is indeed fusion of hydrogen into higher and higher elements. And so the high mass star kind of ends up looking like an onion with having a shell of hydrogen and then helium and then carbon. And then you go to higher and higher atomic numbers that you see in the chemical element table until iron is reached. And so the thing with iron that makes it special is that it cannot fuse and produce energy. So at that point, the gravity will win because there is no, as it says here, countervailing force, which was the energy or the radiation that was produced by every fusion process that created that onion shape, onion-like structure. And so the gravity wins at that point, and it's just the core of the star. And so now, if we were live, I would probably have been inspired to bring a basketball and a tennis ball. So now here's what you can do. If you feel so inclined, you're going to think of it as, okay, the basketball is the core of iron of that, whatever was left out of the star. And then the tennis ball is a tiny bit of a shell. Now drop all of them together and you are going to see how the tennis ball is going to be shocked and is going to be ejected so much higher in space. So this is a really good analogy of what happens in a supernova explosion. So the core of iron is going to collapse under gravity. So now inside, yes, there is compression, which is going to have a lot of atoms being smashed onto one another. And yes, there will be some nuclear reactions, but no fission or fusion. There will be some breakage of the nuclei and a lot of neutron captors that are going to break all those nuclei into pretty much everything, whatever is going to be left, thanks to that nuclear force reaction, is going to be a soup of neutrons. Well, if there are enough neutrons, then gravity is going to win even more, and it's just going to compress them into oblivion, because we don't know what it is inside the black hole, right? Not the supermassive one, but the black hole, the stellar mass black hole. So again, it's all dependent on how much mass this star starts with. So there is a limit, and these limits have been calculated. There's a limit. It's just if you have more than a certain amount of neutrons, then that the gravity is going to win and is going to compress them into a singularity. There is no fission because that means you have a breakage of higher mass nuclei like uranium. So the uranium is not formed in stars. It's actually formed later on during the supernova explosion, but later on in the history of the universe, after the interstellar medium has been enriched with elements other than hydrogen and helium. And so that's what happens in the nucleus. And then because of that kinetic energy, the energy of the shock itself, that is going to create some other reactions that people like nuclear physicists or astrophysicists are still studying and trying to calculate the probability of this and that reaction to happen, and explain to us all how we got to have all this universe enriched to this much uranium or this much other elements that we know exist, but we try to understand how they came to exist out of a universe that just started with hydrogen and helium. So I don't know. So I try to break it into a few things, and I think I addressed at least a few things in this question, but feel free to ask for a follow-up. So it is both a matter of, yes, gravity overcoming any countervailing force. And the countervailing force was just before the iron was produced, was the radiation that was coming from the fusion process. Usually was hydrogen to helium, helium to carbon, and then nitrogen, oxygen, and keep going towards the iron. But then the iron was special because iron, if it fuses, it's going to eat energy. And so there's nothing to keep up, to counteract the gravity. And so the gravity wins. I think, yeah, we can go on. Maybe there's a follow-up from Frank, right? Like when you say something is X times brighter than the sun or the moon, does that mean that the light lies beyond the frequencies we can see with our eyes? So there are quite a few things here. When I say it's brighter, it's the intensity of the light. And I probably referred to the light that we measure with an optical telescope. It turns out that anything that is at higher temperature actually has higher intensity of light at all of the wavelengths. That's called Stefan Boltzmann's law for black body radiation. So, for example, a hotter star is bluer because it has a lot more blue light than the red, but even in the red part of the spectrum, infrared or radio, it's still more intense than the light that is emitted by a cooler star, which appears redder to us. Does this make sense? So it is not necessarily the frequency of the light, the type of the electromagnetic radiation. It is definitely more intense at all frequencies. So that's what I meant by brighter, like the overall bolometric, like over all of the wavelengths, it is more energy altogether. So that makes it brighter.
Thank you, it's very helpful.
Great.
Dr. Constantine, I have a question, but this has nothing to do with your talk. I want your opinion as a physicist. Why is it that Stephen Hawking never won a Nobel Prize?
Oh, I'm not sure that's a physics question. That is
it a politics question? His discoveries in the area of black holes, particularly in information loss, seem to be seminal and profound, but he never won a Nobel Prize, and so now he'll never get one because he's dead.
Yes, I totally agree with that. But what I can offer here are just my 2 cents or my opinion, right? Of course, I don't think we can.
No, that's all I want is your opinion.
Okay, so here's why I think he was not. I think he was on a list of the possible nominees for a long time for the Nobel Prize, but his predictions were mostly theoretical, and I think he would have been included in this year's, in the 2020 Nobel Prize laureates. But in general, for just theoretical results, I don't think so it's kind of hard because they don't have experimental evidence. They don't have real evidence. They're just mathematical models. And I think that's what Stephen Hawking had, right? Because we are actually not going to be able to detect the radiation, the Hawking radiation that he predicted. So he made great predictions, but we're just not going to be able to measure that kind of radiation. It's sort of like the string theorists, they have wonderful mathematical models for what happens at the edge, at the social radius of a black hole. But I don't think they have a consensus, but even if they had some consensus, we don't have the tools to test those predictions. And so I think there is a tendency, especially with prizes like the Nobel Prize, to stay away from pure theoretical predictions and favor things that are more palpable. And I think it definitely helped, the measurements that Andrea Ghez and Reinhard Genzel put together, which proved beyond doubt that there must be a supermassive black hole in the center of our own galaxy. So I think it was the experimental result that linked the theoretical predictions to this discovery, to the idea.
So I guess if you're a theoretical physicist and you predict something using theoretical physics, and unless it can be proven in your lifetime, you're never going to get a Nobel Prize. If what you predict with theory can't ever be proven in your lifetime, you'll never get a Nobel Prize.
I don't think so. Yeah, unless we change the way we see things as a society, maybe.
Okay, thanks.
Sure.
Anca, there was another question toward the end. It comes after the discussion about luminous flux. It says, will everything in our galaxy, I guess theoretically, end up in this black hole?
Oh, well, everything in, oh, okay. Right, so thanks for the question. That kind of goes into black holes don't suck. So basically, there could be black holes around us, right? Trillions of them, sort of like the neutrinos. We're never gonna know about them, because in order to feel the sucking power, the gravitational field of a black hole, you really need to be really close to its edge. We call that event horizon, right? Or the Schwarzschild. Not going to be feeling that strong gravitational pull, right? And you're just not going to be sucked in. As I said, if we just put the same, a black hole that has the same mass as our sun in the location of the sun, our orbit as a planet or any other planet, even Mercury, will be unchanged. So yes, the thing in the center is not going to offer us the light and the warmth and everything else we get from the sun, everything else but the gravitational pull that keeps our planet together. But from the perspective of the gravitational pull of that mass alone.
Oh, is she frozen?
Let's hope that the video feed comes back here. There was just a pause there.
If I could offer a comment.
Go ahead, Bill.
The third recipient of the 2020 Nobel Prize was Roger Penrose, who is a theoretician and was a mentor and collaborator with Stephen Hawking. So although Hawking didn't live to receive a Nobel Prize, and it would have been a terrible problem because they limit it to 3. So I don't know how they would have managed it. But Penrose did receive a share of the Nobel Prize in 2020 for the theoretical work that he did with Stephen Hawking.
Thank you, Bill, for the comment. Actually, I was a bit cut off here, so I did not catch the whole thing. So do I hear that you're kind of agreeing with my 2 cents that Stephen Hawking would have, I think he would have been included. I mean, it was technically included, but obviously he's not with us to feel that, to see that.
Right. There are plenty of theoretical physicists who are on the list of Nobel laureates, but it is a matter of living long enough to have your work recognized. And sometimes it happens quickly, as with the discovery of gravitational waves, and sometimes it's a long delay.
Right, but so don't you think that's still very much related to the experimental results, to the advances of technology that allow for testing those ideas?
Absolutely. I think Sandy Conrad asked the question about would everything end up in a black hole, and I think your answer was very good. But there's so much real estate in the universe that unless you're, depending on how you think about it, very lucky or very unlucky, you're not going to blunder into a black hole.
I mean, these things are tiny, right? And so, right. I mean, because of all that real estate, it's going to be really unlikely to stumble across one, basically, right? So yeah, that's why we need to be kind of smart in our searches. And we said, okay, well, we found some hints for the fact that in the centers of galaxies there are these things. So yeah, let's study those, and maybe if we understand a lot more about how they work, why they're there, then we might look for them in some other places, and we're going to be armed with the tools to find these things somewhere else. But it's very likely that they are even in the room with us, some tiny micro right, because they're called primordial black holes, so they can be pretty much anywhere, but they're just so tiny, they're just not going to tiny in size. Even, I mean, of course, the size depends on the mass itself. But if the mass is small, then if they're black holes, they're like pinpoints, or a fraction of a pinpoint in size. So yeah, they can be anywhere, but they're not going to suck anything in.
I have a question. Do all black holes have the same density? And within a black hole, is the density consistent from the core to the outside? Do we know?
Thank you, Melvin, for the question. I don't think, I mean, well, the truth is we don't know what the black holes are made of. So we might be able to put a limit to the density. It's not going to be the same density. Obviously, that depends on how much mass is concentrated into that singularity. And so even though the black hole itself is a singularity, we can define a radius of, as I said, the event horizon, the Schwarzschild radius, a distance from the singularity where anything will still survive and not be sucked in. And so there is a limit of the density, like, maybe above a certain number, there is basically nothing else that we as scientists know of that can explain what that is. So in that sense, we can talk about density, but I don't think we know much more, other things than that about what's inside a black hole.
Is there any possibility that the essence of a black hole is the exact inverse of the essence of whatever it was that gave rise to the Big Bang?
So that's a great question. I think people definitely ask themselves this, and there are mathematicians who try to model that, right? And I think that's where the idea of a white hole comes from, and the wormholes. But and I guess we or the mathematicians or the theoretical astrophysicists, they can speculate about them, but it's going to be really hard to test any of these theories. And it's not just one theory, there are quite a few, and they're fun to work with. But to date, we did not find a way of basically beating light at its energy and at its speed, right? Because everything that's going to go into the black hole to find out what is in there, it's going to be sucked in. And so we don't have information. Nothing is going to escape to bring back to us that information. So we don't know. So, I mean, yeah, that's probably a convoluted and long answer to that. I definitely don't know the answer to that. But there are mathematical models that can say that's a possibility. But I don't think we're going to know soon whether that is the only possibility. So those are still kind of in a fantasy land, all these ideas.
When when you refer to information, my understanding, I don't have any technical knowledge about this, is that information is used in a somewhat technical sense when you're talking about black holes and all. And was it Hawking that, I mean, one of the, as I understand, conundrums is whether information in that sense can in fact be totally destroyed. I mean, that's, in other words, if the information goes into the black hole, it no longer exists, no longer be measured or something like that. I don't quite comprehend what they're talking about. But.
Well, so I don't think we know how exactly the destruction process works, right? What we know is that it's lost. If anything falls onto a black hole, we're just not going to see anything, right? That's what we mean by information. We're not going to have light coming back to tell us what kind of energy or wavelength or frequency or direction of motion, speed. We're just not going to have any information like this, or time, right? The time actually, so the actually, when you think of it, when things fall into black hole and say we witness such an event, it's going to, because of the relativistic effects, the time dilates, and it's going to look to us so that, yes, the thing speeds up, but then at some point it's going to slow down and it's going to just stay there at the edge of the black hole forever. And that's all that we can get so far. And mathematics tell us the same thing. It's,
wow.
We don't even see the things falling like into the event horizon.
Well, thank you for telling me that the experts don't know more than I do.
I think that's normal. I think I mean, we get some answers in our investigations, but I don't know, at least from my experience, every answer comes with a new set of questions.
Exactly.
So,
Right. Thank you again.
oh, you're very welcome. Bill, I think you have a lot more time than I have to maybe read about all this wonder. I mean, you know, I'm at some point I'm going to read some more about the white holes and wormholes and or what's exactly happening, or what the mathematicians I don't know, discovered lately that's happening at the event horizon of a black hole. What more? You're muted.
I think you've done a wonderful job of presenting this subject. And if someone really wants to invest a little time, it would probably be good to watch the movie Interstellar if you have not watched it, because Kip Thorne was a consultant for that movie. And I think they tried to do a good job of not contradicting known science, but there's also some speculation and a storyline there that people might find interesting. So it's not called The Black Hole, it's called Interstellar. And it's probably
there is
5 years
another,
old
I
now.
think there is another movie that's called Black Hole. Or
Yeah, there is, but I would say Interstellar is
yeah, it's
I
pretty
can
good. That's
recommend
true.
that. Yeah. But thank you for your presentation.
Well, thank you, Bill, for your kind words, and thank you all for the questions.
Oh, thank you so much. It is
Thank you,
mine.
Sandra.
Thank you so much.
Oh, it's great.
I learned a lot.
Oh, you're very welcome. I'm hoping. I mean, yeah, in real life, I would have definitely encouraged you all to interrupt me and ask questions. It's kind of hard this way, but and I do know I do have the tendency to slip into using jargon, so I hope I didn't use that too much.
And Dr. Constantin, I want to thank you too. I know here at the end of the semester, your time is especially valuable and precious as you wrap up everything with our undergraduate students to make sure that they get all their projects completed and you get everything graded. So I really appreciate you giving us this hour and a half today. And you remind us all that the universe is a fascinating place. And as Frank mentions, a lot of discoveries still to be made. So thank you for your time, and thank you for sharing your expertise and bringing us a little farther along in our understanding of these galaxies.
Oh, thank you. Thank you. It's always nice to have people interested, to know about people who are interested in learning more about our universe, and yeah, discussing with scientists. We're kind of lonely where we are sometimes.
Well, we appreciate you, and we appreciate everyone who joined us today. And friends, take care and be well until we see you again next week.
Yeah, take care, everybody. Bye.